So now let's look at this theorem where it helps you to find sufficient statistic. Okay, we call it factorization theorem. So basically, like here, U in the statistics is built based on y1 to yn. Okay, so this is the thing. It's just a function g of y1 to yn, and then we say U is a sufficient statistic. Okay. Which is the original definition, basically that the distribution of y1 to yn given U not depends on theta, right? But this is an important tool for you to find sufficient statistics where you just if you can factorize, okay, you can factorize in this fashion. So basically, let's say if you have function L theta, which is your likelihood function, and if the L theta can be factorized by say G of U theta and time with a function which not depend on theta, okay, H of y1 to yn. So basically, like if you can factorize that way, okay, and then like all information here can be wrapped in this U, okay, it can be wrapped in this U. So this is H here is a function not depends on theta, okay. It can be constant, it can be a mix of between y1 to yn. I don't know, okay, it can be anything. But this basically this term does not contain theta, and this term contains theta, okay, this term contains theta. So for the term contain theta here, the U go with that term, okay. U here your function from y1 to yn here. This will be a sufficient statistic, okay. Then U will be a sufficient statistic, okay. We do have the proof of that, but to save some time for other part, I will just skip the proof, okay, and in this way we can have more time for other part, because otherwise thing will get in very slow, okay, very slow, and we don't have time for all the section I prepare here. Again, this is an important course, so I'm a little bit ambitious in a sense like I try to give you like a little bit of everything, okay. So you can eventually say if you go to more advanced level, you can look at and deeper, or maybe also know like there are some tool right available, and say if you need to make a certain thing from your own research, and you can always revisit, right, visit back, go back to look at it. So basically, like again, if you can factorize in this fashion, okay, a function not depends on theta, and something else that go with theta, and that basically theta is called this U is called a sufficient statistic, okay, for theta, okay. We have a proof in the notes, okay, for the discrete case. For the continuous case, more involved, okay. But if you are curious of the proof, and then you can refer to the note I already uploaded, the note for the discrete case, okay. But in any case, let us just walk through some examples, and you know how to find sufficient statistic, okay. There another version we call the multivariate version, right? So here, like you have U1 to U2, okay, and for sure, if you this is for the one U equals sufficient statistic, okay, and here we have another card called like Jointly sufficient statistic. For sure, you can also make the U1 to UN too, right? So in the case, say you have like the estimator is you estimate like say the theta in this case like two things, right? Like both theta 1, theta 2. So for example, if you look at the normal distribution, theta 1 can be the mu and theta 2 can be sigma square, right? So if it will be you have a jointly sufficient statistic, okay, for theta 1, theta 2, if you can factorize in this fashion, okay. So basically the same thing, right? A function which not depend to any theta at all, and a function where you have thing go with the theta 1, theta 2, okay. So at that time, the U1 and U2 we call the jointly sufficient statistic for theta 1, theta 2, okay. So in that case, you have like two parameters, and for sure you can extend to the n parameter, right? Other m parameters, okay, for multi-dimension case. So let's look at the example. So again, it's just pretty much the same fashion as what we saw before, right? So say, suppose we're interested in estimating proportion of Chattanooga um, uh, allergic to nuts, right? And a sample of n Chattanoogans, right, is of 10, right? So in this case, and basically like now we try to model, right? So one kind of easy way to model is that like we model each person will formally Bernoulli P, right? P is true proportion of Chattanoogan allergic to nuts, right? So say like one person like Philip, right? He has a complete data, y1 to yn equal, so for each observation he has that, right? While Aaron, she only know the total number, right? With not allergic, right? So one person has like the exact data for each observation, and one person has just the total yi, okay, summation, okay. So to estimate p, right, like the Philip information does not give him more advantage than Aaron, okay. So in this case, basically like the message here that like for this case, actually you have the summation here is already a sufficient statistics. So basically, in order to estimate p, you don't need the whole information here, right? Basically, you just need the summation. It should be enough for you to estimate the p, okay? So let's look at why is the case here. So if you look at the factorization theorem, you will be able to prove that u, in this case, the summation, okay? In this case, u is a summation, right? Because we say that Erin, she doesn't have any more Philip, right? He does not have any more advantage than Erin, right? So in this case, you can see that basically the message here is that like basically like if I already know the summation, and then I don't get anything more from, if I have like y1 to yn, okay, that information. So in this case, which means like the sigma yi here is a sufficient statistic to estimate the p, right, for p, right? So and then like let's look at the factorization theorem. So basically the goal here that in order to show you a sufficient statistic, right, we can apply this tool, it's very powerful tool. So basically, like we should be able to segment, okay, the L here, the likelihood function here, to the G of U theta and time with something which not depend on theta, right? So first thing first, we need to write out the likelihood function. So here, like we just write out, right? So today is the 5th, okay, March 5th. Okay, so the y1 to y2 to yn, okay, given p, okay, in this case, theta p will be just basically you can remember that each is the product, right? Because we have independent y2n p of yi, right? Y minus p of 1 minus pi I, right? Yi, I'm sorry. So this is a PDF of the Bernoulli, right? So remember, recall that since y1 to yn independent, right? Observation, and the BMF of the Bernoulli, right? Y must be 1 minus y, okay. This is a PMF of Bernoulli P, right? Bernoulli P. So with that, right, we can collect all the term here. The product here, basically, it's just like the summation here will become yi, right? Yi. And then it will become 1 subtract p, and you have n, right? If you collect all of them, n subtract yi, right? That's this of n, I'm sorry. So you can make it this so you can see that, right? You can see that this is, you can think this E, maybe you can denote, okay? I can denote that, right? I can denote sum of yi, right? I from 1 to n equal to Sn, okay? The summation Sn. So basically at that time I can write my likelihood function A by theta p to the Sn, right? Y minus b n subtract to the Sn, okay? And this is basically you can think that this guy, is a G of, right? I put a U, okay? So I put U for consistent, okay? Maybe I put U here, right? S and a U, it doesn't matter here. U, okay? So this is my GUP, right? And another function which is 1, right? 1 is just my H, Y1 to Yn, right? Okay. So basically, like now we apply the factor. So basically, the factorization theorem, it tells us, right? If you can segment this way, right? G of U theta and time to H of Y1 to Yn. So in this case, my H here is 1, okay? And this is my U, okay? U here, okay? So basically, at the time U, okay, I from 1 to N is a sufficient statistic, right? Sufficient statistic of P, right? P, okay, P. So basically, like the main task is that like you write down likelihood and then you collect all the term which go with the model parameter in one place, right? And this is called your G function. And the other term which is not include the model parameter, which is your H function. And if you can do that, and basically like U will be your sufficient statistic, okay? So this is the fact from a factorization theorem, okay? Factorization theorem. So this is one very powerful tool, right? Because, for a certain goal, when you collect the data, you have a certain goal, right? And with your given goal, okay? So how much, what information you should retain, right? You should collect, right? Because sometimes, storage, the whole data will be a big issue. Also like collect, the data at the fashion you want, also a big issue, right? So you have to navigate in a smarter way to get the data, right? Yeah. Maybe store it, the data, okay. Question, yeah. Good. Okay. So let's look at another example. So here you have like y1 to yn, okay. It's from exponential family, right? 1 over theta, exponential of yi given theta, okay. So here like you have theta is non-negative for sure, right? So show that y bar is a sufficient statistic, right? Sufficient statistic, right? Of theta, okay. So we just work more and more example, and from that we get used to the concept, and be able to do similar tasks, right? So here the same story, right? You just first write out likelihood function. So you can L of y1 to yn, even theta, right? Just product. Yeah. So now at that point, you should be familiar with this procedure. Okay. Yeah, this is a typical procedure when you write down the likelihood function. And because this is like this, right? So it will be 1 over theta I from 1 to n exponential of, right, negative yi by theta, right? And here for sure, if you want to put a constraint 1 yi greater than 0, it works too, right? So maybe for completion, okay, I can also put 1 yi greater than 0, right? Which is indicator function, right? Indicator function. Okay. So it'll be 0 if yi negative, right? I can put that for completion because basically here it's just that function, right? If negative, then you get 0. If positive, then you get that much, right? But this term won't affect anything, right? Won't affect anything. So it will be like 1 to theta to the n, and then you have exponential of, right, summation of yi, right, by theta, I from 1 to n, okay, and 1 up yi. So basically, like now the minimum value, right, the y1 greater than 0, right, because each of them are non-negative, so which means the minimum is non-negative, right, non-negative. So basically now you can see that each can be written by this, right? Theta to the n, then exponential of, right, n of y bar, right? Y bar, right? By theta, and times this function, right? Y1 non-negative, right? Is it equal sign? So you can see that this is your h, right? Your h function, y1, yn, right? And this is your g u theta, right? U theta. Here like u equal to the y bar, right? Y bar. So which means like from the factorization theorem, right? So basically from a factorization theorem, factorization. So which means from star here, right? Star factorization theorem, right? From star, right? Maybe apply the factorization theorem to star, right? Apply to star, right? We have that y bar, okay, is a sufficient statistic, right? Sufficient statistic for theta, right? For theta, right? Theta is sufficient statistic. So here you have function, just two things, right? U and theta. So which means like you have a sufficient statistic in this case. And again, because the summation and the mean, it's just a one-to-one transformation thing, right? If you have summation, so which means you have a mean, and you have the mean, you have summation. So basically, like if you have one-to-one transformation, they also like if one guy is sufficient statistic, which means the other guy also sufficient. Okay, you have such a one-to-one, okay, transformation. Okay, so here like right, so here like from that you can see that if you say if you have the y1 to yn, right, represent listening time, right? So basically like how people apply, right, to a new lyric, right, a minute for n listener, right? So the time someone way then can model is using exponential distribution, okay, with parameter theta, so which represent the average time that listeners typically engage with the song, okay? So again, we with that, and we can model by the PDF function like this, like previously, right? So suppose that the set has a size of n 100,000. To estimate that, right? Do we need to store all the observation information, right? Or not, right? If not, then which information need to be stored? So again, with that, right, you can see that example 945 here, y bar is sufficient statistic for model parameter theta, right? Already, already know that, right? So which means like with this task, right? Given task, right? Basically like this data set 100,000. But instead of you look at all of them, right? You just keep the mean. It should be enough. Should be enough. The y bar should be enough. Should be efficient enough for you to estimate the theta. You don't need the individual observation. So just like the same example, like the nut allergy, right? Nut allergy. So basically, like you just need the sum or the y bar, right? It should be enough. It should be enough. Yeah. So this is how you see, like, the information, it can be stored in a certain way where, um, it still help you to achieve your goal. Yeah, your goal. Okay. So this is a kind of a very smart idea, right? Instead of you keep the whole, right? Like you eat the whole orange, or you just take a juice and eat it, right? Drink it, right? Any questions? Good. Okay. So let's look at another example for the case of a normal, okay, which is normal because like the normal is the kind of distribution where we use a lot, right? We use a lot. So here, like you have the data, right? You can model anything with normal, but here we make it general, right? Just consider normal, but for sure you can model anything, right? A lot of things with normal. So here in this case, you have a normal random variable, okay, and it's from mu sigma square, okay. So there are three cases, okay. One case, mu, and sigma, okay. You know the variance, and you don't know mu, okay. So you need to prove that basically, like at the time, y bar will be sufficient statistic for mu, okay. In the case, already sigma square. The second case, if you don't know sigma square, and then basically like uh, sigma I subtract mu square will be sufficient statistic for sigma square. Okay, you can get the 1 over n below, but it won't affect much. Okay, it won't affect because it's 1-to-1 again. So at the time, the basically like you can think like the sample, pretty much like the sample variance, right? Other a sample standard deviation. Okay, it doesn't matter because they all 1-to-1 transformation. Okay, so they will be a sufficient statistic for sigma square. Okay, and if you have like both of them not known, okay, so basically like the joint of y bar and the sigma s square, okay, but again, you can show that y bar and sigma n here, n square, and also 1-to-1 to the summation of yi and sigma yi square, okay. So that time, basically like we go with summation of yi and summation yi square, okay. Uh, jointly sufficient for mu and sigma square, okay. Jointly sufficient for mu and sigma square. The third case is more like it's up with the multi-rate factorization theorem, okay, version, okay. Just a demonstration for the multivariate version. So here in this case, you have like two model parameters, and A and B, you have just one. Okay, it's one because one is known already. So let us work on this problem. Okay. So basically, like again, you always, when you work with a sufficient statistic, you always first write the likelihood. Okay. So it's a criteria, right? Yeah. But it needed. So first I just put like this way, okay, and then eventually like for sigma known as mu known, both of them unknown, and then we make it specific later, okay. So we will like p of I from 1 to n, 1 of sigma, right, 2 pi, right, and then exponential of yi subtract mu square by 2 sigma square, right? Okay, this is how you do it. And then it will be the product, you take the product, right? Sigma to the pi exponential of summation of yi subtract mu square by 2 sigma square, okay. Okay. Okay, so for the first case, right? So now I did have that. So the first case, so when so by A, okay, so part A, so this is a whole, okay, part A. A, they said like sigma square non, right? So basically they may be equal to one, okay, sigma square non, okay, sigma square non, 1, 2, 3, which is a fixed number, right? So at time like my likelihood function, I can written like this, mu sigma square. One sigma 2 pi. Okay, so this thing is just a constant. Okay, so I maybe I just put proportion, so I can throw it away. Okay, I can throw it away because it's a constant. Okay, a constant which is it's just proportional to. Okay, so I can throw that. Basically, my goal is that I want to throw the constant part away. Okay, the constant part away. So it will be proportional to. Okay, which is proportional to. Okay, proportion to. Okay. Okay, so basically, like it's kind of a pretty much like alpha. Um, right? How you know do the notation, right? So it will be proportional to I think this is how they do that. Okay, to this exponential of right exponential of um 1 minus 2 sigma square. Okay, uh, um, and then summation of okay. Now I do a little bit trick here. I from 1 to n. Okay, subtract y bar. Okay, so basically I insert and I add and subtract y bar, right? But after I do that, so let me make it step slow a little bit. Okay, y bar subtract mu. Okay, okay, okay. So I just add top on the y bar, and then I subtract the mu. Okay, so in the middle here, I subtract y bar and I add y bar here. Okay, in the middle. Okay. So nothing new here. And then basically, like you can write it, right? Which is this thing will equal to this. We did many times already. When you do for the s square, right? The s square thing, right? But basically, it's just nothing else than this guy. Y square, okay, square. I from 1 to n, okay. And plus, okay, plus n of y bar subtract mu, okay. You can verify that, okay, easily. Okay. So basically, like this hole here, you can write it. The cross one will be 0, right? Cross one will be 0. Because if you do a summation of yi to y bar, I from 1 to n, it will be 0. Okay. Clear? Good. Okay. If you're not clear, just do some, write out, and you collect a term, and you should be able to see it. Okay, so yeah, we go to the fun part now. Yn given mu, okay, because sigma non already, which is proportional to this guy, right? This guy exponential of I just rewrite this term. Okay, so and you see how we separate them out, right? I from 1 to n, subtract y bar. Okay, subtract 1 sigma square n, right? N here, y bar subtract mu, right? So nothing else, nothing, right? I just uh plus this guy here and this one. So which mean like this guy equal to exponential of I put it here, 2 sigma square y, I'm saying mu, right? Square time exponential of 2 sigma square, right? yi square, right? Okay, so I reverse the reduction, right? But this guy basically is just my h function, okay? H yi, y2 to yn, right? And this guy is my g u mu, okay? Here the u equal to y bar, right? Y bar. So which means I put like y bar, okay? So I just put y bar here, okay? Right. I mean, if you get used to that, well, u y bar doesn't matter, right? Doesn't matter. So y bar is a sufficient, okay, statistic for mu, okay, for mu, okay. You can see that, right? So the trick here is that like you play around a little bit and you push, you flush all the guy out from H, and another one you get the G, okay, G. Clear? Good. Okay. So similarly for B, right? When you have mu none, okay, and sigma unknown, right? So at that time, there you have to play around a little bit, right? It's slightly different with what we did before. So in this case, sigma square none, right? So you basically you can think like this term is constant, the first term constant, and you throw him away, right? But now because mu none, okay, sigma unknown, sigma the goal of estimation. So for sure you cannot do this proportional strategy. You need to write out this term, right? Because it's something you need to estimate. Okay, so B here, mu none, okay, and sigma square unknown, okay. So the goal here is that estimate sigma square, right? So again, you just write out the likelihood function. Yeah, always like that, okay. It's a very important function because basically in some sense it just tell you like how likely you observe such a data, right? Sigma 2 pi to the n exponential of 2 sigma square I from 1 to n yi subtract mu, right? Square. Right? And then let's see. The first term you cannot throw it away like last time, right? Because you do need it. And here, oh, but this already there, right? So this is basically like yeah, I think that's it, right? Yeah, sufficient statistic, right? I guess that's good. Okay, even better. Exponential of t, right? maybe say t. Here I didn't know, maybe u, I put u, okay, whatever, u, okay. Here u equal to u, okay, I put small u here. Okay. Here u equal to summation of I from 1 to n yi subtract mu square, right? Because in this case, because you know mu is known already, right? Yeah. So in this case, this is your g u sigma, right? Sigma square doesn't matter. Right. You can put this guy under the here, and you get a 2 sigma square, okay? Square root here. So this guy is just a function of g u sigma square, right? And this guy is 1, right? Times 1. So basically like your 1 here, right? Which is your age of y1 to yn, right? So from the factorization theorem, it tells us, right? Factorization theorem. It tells us like the summation of I from 1 to n, yi subtract the mu square is a sufficient statistic, right? Statistic of sigma square, right? Sigma square. So this is even more obvious, like than the previous one. Okay, the previous one. And lastly, which is the case both like mu sigma unknown. Okay. So C, which is mu unknown, sigma square unknown. Okay. So again, you just write down here mu sigma square. Okay. I mean, theta in this case will be sigma square, right? Sigma square. And theta in this case will be both of them because both of them unknown, right? Another time you can write this guy by exponential again to I put here. Okay, sigma is, and here you have exponential of again, I just rewrite the likelihood function first, okay? So always the first step is that you need to write out the likelihood function. Yi subtract mu square. Okay. And then for sure, I can push them all together like this fashion. Because my goal here is that, right, I will show that this first order, right, and second order here, summation here, right, yi summation and yi square summation is sufficient, right? So basically, I need to create something with the thing, right? Summation yi, summation y square, right? So now in order to create that thing, right, I will do a little bit trick here by basically like here just like 1, 2 sigma, okay. So I just what I do, I will break out this the thing in the bracket here, okay. Yi subtract mu square, okay. So if I break out this thing, what I have will be summation of I from 1 to n, yi square here, right? Which means I get like one thing I want. And then will be plus like mu by sigma square. I get another thing I want, yi, right? And then subtract the n mu square by 2 sigma square. At this point, I also bring out this thing in exponential, okay? So if I bring it out to the exponential, basically like just exponential log, right? So it'd be subtract here, n log of 2 pi sigma squared, right? Right. So log of that, right? And remember you 1 over, right? You 1 over, so it's just negative log of that terms. So if you didn't know this guy is by the v, okay, you can denote this guy by v, this guy by u, okay. You denote this by u, the summation of the first order here, the second here is v, the first is u, okay. And you can rewrite by this fashion, right? You can rewrite by exponential of 2 to the v plus mu to sigma square to the u, right? Subtract n mu square by 2 sigma square and subtract n log of 2 pi sigma square, right? So this is basically, it's just a joint function, right? U1, right? So you remember in the multivariate case, right? If you have a joint function like this, right? U1, U2, theta 1, theta 2, and time something, right? And that's something here, in this case, with just 1, okay? Just 1. So at the time, so basically at the time, you have U and V as a jointly sufficient of mu and sigma squared, right? So basically because of the factorization theorem, right? So the multivariate version, multivariate factorization, it gives us, right? Gives us UV, right? Is a jointly sufficient for mu sigma squared, right? Here u equal to the summation of yi, I from 1 to n, and v is summation of yi squared 1 to n, okay. So we did prove that, okay? We did prove that. But you also should know that the UV and S way not, okay, not here. We have a UV and YI S square, okay. It's a 1-to-1 transformation, okay. 1-to-1, okay. So which means if UV is sufficient statistics, and at that time Y bar S square also sufficient statistic, okay. So which means like this one also jointly sufficient, okay. So if we have a 1-to-1 function transformation, okay, like that, maybe like if one is sufficient, this one also is sufficient, okay. So you have more than one sufficient statistic, okay. You have one more than one, okay. Any kind of 1-to-1 transformation of sufficient also sufficient. We do have a small proof for that in the note as well. So if you're curious, you can also look at the proof, okay. Okay, so we stop the class here.